Okay, so the next couple lessons that we are going to talk about are graphing. Graphing is really important in physics because it's another way that we can demonstrate or show a relationship between two different variables, or we can kind of take a look at a graph and describe what's happening to an object based on what the graph kind of looks like. So in physics, in the next two videos, we're going to break it down. The first thing we're going to talk about here is distance-time graphs, and that's what this video will be talking about. The next video, we'll talk about speed-time or velocity-time graphs. The tricky thing about graphs is it's really easy to get these two confused. So they're two different things, two different lessons. Keep them separate. So today, our main objective is to take a look at how we can use a distance-time graph to calculate speed, and that'll be the whole point of this. Okay, so distance-time graphs. We'll start off with the basics. I can use this graph to represent the motion of a person or an object or something like that. First thing, very important right here, I always want to make sure I put my variables in the right spot. So distance or position will always go on the y, and the y is the vertical or up and down, whereas time will always go on the x-axis. So down here at the bottom, we're always going to have time as horizontal, position or distance as vertical. So here I have an example of a graph. You can see the line on the graph right here in kind of purple there. I want you to take a look at that and think about what would you say if I asked you to describe the motion of this object. So at a time of 0, right here, I can see the object is sitting at a position that would be 5 meters away from the origin or from where it started. At a time of 2, it's still sitting at 5 meters. A time of 4, it's still in the same spot, 5 meters away, 6, so on, all the way kind of to the end. So this whole entire time, the object is sitting at 5 meters away from the origin. So I could fill this in. At a time of 0, the position is 5 meters. At a time of 2, the position is still 5. At a time of 4, it's 5, 6 is 5, and the trend just continues. So at the bottom here, the question, how could you describe this object's motion? Well, is this object really moving? If I have an object that's just staying at 5 meters the whole entire time, the answer would be no. So I could say it's not. It's at rest, or it's stopped, or it's not moving, something like that. Okay, let's take a look at another one. This time, rather than that line being horizontal, I can see that it's at an angle. At a time of 0, so at the very beginning, the object is at a distance of 2 meters. At the end, at a time of 8, you can follow that up and over. At 8 seconds, the object is also at 8 meters. So I want to know how fast is this going, and how we're going to do that is with an idea called slope. And slope is a way of measuring basically how steep a graph is. So we can use two different formulas. First one, slope is rise over run. So how much did the graph change kind of vertically versus how much did it change horizontally? Another way I can write that is like this. Slope is a change in y over change in x. Really, those two just mean the same thing, because my rise is y, my y-axis, and my run is my x. Another way, if I'm talking about a distance-time graph, I could also say slope is the change in distance, because distance goes on the y-axis, over a change in time, because time always goes on the x-axis. So kind of three different formulas. I would mark any of those correct. You could use any of them. It wouldn't really matter. So you can take your pick. I'll probably always use the third one. We'll see. Okay. Very, very, very important. When I'm calculating the slope of a graph, I'm not just calculating it for fun. Like, there's a reason. When I'm calculating the slope of a position and time graph, we already said that we know slope is rise over run. My rise is a change in distance, and my run is a change in time. So if you take a look at this formula here, change in distance over change in time, hopefully that looks familiar to you, because that is the formula for velocity. I know the formula for velocity that we talked about a few lessons ago is change in distance over change in time. So I can say if I calculate the slope of the graph really all I'm doing is calculating the speed or the velocity, and that's what this is saying right here. The slope of a position time graph is equal to the velocity. So now that we know that the slope of a graph, of a position time graph, is equal to the velocity, let's take a look at this practice problem. So the practice problem says match the terms at the bottom. So at the bottom I have these four kind of terms or definitions there, and I want to match them to different sections or segments of the graph. So segment A, I have the graph labeled A, B, C, and D. So what I'd like you to do here is pause the video, on your piece of paper match up, what do you think section A of the graph? Does section A of the graph represent an object that's going forward fast, staying still, just moving forward, or just moving backwards? So again, pause the video, finish this practice problem, and then I will give you the answer. Okay, so if I know that slope is equal to velocity, that means the steeper the line, the faster the object is moving. So if I take a look here, my object that's going, section A means it's going forwards. My slope is up and to the right, so it's going forwards. But C, right here, is also forward. So both sections A and C mean that an object is moving forwards. I need to decide, well, which one's faster? And I can tell that by looking at the steepness or the slope of the line, because C is quite a bit faster. So that means I can put this forward fast by C, and A would just be forward. Now I can look at the other two that I have. Section B right here is straight across. That means that that object is staying at 4 meters the whole entire time, so it's not moving. So that's staying still, which leaves me section D as being backwards fast. And I can tell that because the graph goes down. Anytime my slope is down, that's like saying an object's moving backwards. Because it starts up here at 9 meters, it finishes down here at 1 meters, so it's coming back towards the origin or going backwards. Okay, another example here. What I want you to do is now the opposite. So now we've taken a graph and kind of described them. Now based on the description, I want you to draw a picture of each of these graphs. So pause the video and do this individual question. Okay, really quickly I'll give you these answers. The first one, so I should have, first of all, I can have 3 axes, something like this. All of them are position time graphs, so I'll say a distance and a time, distance, time, and distance, time. The first one tells me I have a sprinter that is at rest before a race has even begun. So if you're at rest at the beginning, means your distance is 0 the whole entire time. So there would be my first one. Now the sprinter steadily changes their position from the starting point. So they're traveling at what we would call constant velocity, moving forward, something like that. So all I'm looking for there is a graph that slopes upwards. Now, once they get, say, halfway through or something like that, they're going to turn around and come backwards. So this means they're coming back towards the origin, and the third one would look something like that. So there's some examples. Make sure you have those written down. Okay, let's talk about how we actually calculate slope. Let's do one of these. So here I have a position time graph. In this case, the object starts right here. So at the beginning, my time is 2 seconds, and the initial position would be 5 meters. At the end, up here, I end at 10 seconds and 9 meters. So I'm circling those numbers on the graph for a reason. They're going to be important. You don't necessarily have to draw the graph, but make sure you're writing down this part at the bottom with the formulas. Earlier on in the video, I talked about how there's different ways that you can write the formulas. So here at the bottom, I have a couple. First of all, I could say slope is rise over run, velocity is a change in displacement over change in time, or d2 minus d1 over t2 minus t1. So a couple different ways I can write that down. Again, it really doesn't matter. So let's try this one, figure out the velocity. So I'm going to start kind of from the beginning. First thing I'll do is always write down my formula. So here I'm going to say velocity is equal to a change in displacement over change in time. I could write velocity is rise over run, slope is rise over run, change in y over change in x. It doesn't matter. So So I need to figure out, well, how much did my position change? So basically what I'm doing is figuring out what was this change over there. Remember, change in something always means final minus initial. So I want to take where did I end up, which was 9 meters, and subtract from that where I began, which was 5 meters. So the top of my equation will say 9 minus 5. The bottom of my equation will say similar type thing, but for time. My final time was 10 seconds. My initial time was 2 seconds. So there's my equation. So far I have a formula, I have my work, and now I need my answer. So 9 minus 5, I can say is 4 meters. 10 minus 2 is 8 seconds. 4 divided by 8 is a half, or put into decimals like we like to work, is 0.5. My unit, I have a meter on the top, a second on the bottom. My unit is a meter per second. So I would get a full 3 marks for this. I have a formula right here, I have my work, and my answer. Okay, time to try a few more of these. I'm going to give you 2 individual practice problems. What I want you to do here is fill in your givens, start with your formula, plug in your work, and then your final answer. So pause the video here, do this question, and then I'll give you the answer. Okay, so let's go through this one. Take a look at my initials. So my initial position is right here. I have a time of 1 and a position of 2, so I can fill that in. My initial time was 1 second. My initial position was 2 meters. Follow this up to my final point on the graph. My final time was 6 seconds, and my final position over there was 10. So I have those given, so I'm going to start with my formula. I'll say V is equal to a change in d over change in t. This is asking me for velocity, so we're working with vectors. So to get that change in distance, I'm always taking final minus initial. So my final distance is 10 meters minus my initial distance of 2 meters over top of my final time of 6 seconds minus my initial time of 1 second. In this case, I end up with 8 meters on the top. 10 minus 2 is 8. 6 minus 1 is 5 seconds. Now I can take my calculator. I'll go 8 divided by 5 gives me 1.6. I need a unit. Again, I have meters on the top, seconds on the bottom. So my answer is 1.6 meters per second. That's how fast that object would be going. Okay, last practice problem. This graph looks a little different than the one we just saw. Take a look at that. Pause the video at this point and answer this question. Again, you don't have to write down the graph in your notebooklet. Just write down the givens and then solve the question. Okay, answer for this one. Again, I'll start by writing down my givens. My initial position at the beginning, I follow this over. This time my initial distance was 9 meters and my initial time was 2 seconds. Down here my final time is 10 seconds and my final distance was 1 meter. So this graph is sloping down, a little bit different than the ones we've seen before, which means the object is moving backwards. So we should hopefully get a negative velocity if we do this properly. So a slope like this will give me a negative slope or a negative velocity. So start with my formula. Velocity is equal to a change in displacement over change in time. My final distance, 1 meter. So start here, 1 meter minus my initial, which was 9, over my final time, which was 10 seconds, minus my initial, which was 2. here I end up with 1 minus 9 gives me negative 8 meters. 10 minus 2 gives me 8 seconds. So a negative 8 divided by 8 is a negative 1 meters per second. Very important, I got that negative answer, which is what I wanted. That's great because the line slopes down. Okay, so that's the end of the lesson on distance time graphs.